This is the model fit. There's some things you'll notice a little different here. What we find here is that for the GLM function here, we've got the same kind of command here. Left hand side is just the model object we're saving. If we look at further here, with family is binomial, link is logic, and we know that if I just put family as binomial, I don't require to specify the logic link. That's the default. The data is still given as the data frame over here, but in the left hand side, the response here, there's two things here. So we have to combine these two things as one. The first is the number of successes, and the next is the number of failures. So extinct is the number of birds that become extinct, and here at risk minus extinct are the ones that don't become extinct. So these are the two things you require to give here in this command. Be careful, it's not the number of trials we are after, it is the number of successes and the number of failures. Both have to be given here in this case. And the output here is very similar to what we've seen earlier with the earlier model with Bernoulli data. We have the same summary over here with the variables and the p-values, and nothing else changes. As we saw earlier, the null deviance here, altogether how many observations did we have? You'll find the number of observations we had were 18, and here this is degrees of freedom for residual variance is one less because we have actually fitted one extra variable. So the null deviance, actually the null model is where the log area isn't in the model, we just have a constant. And the residual deviance is when we actually have the full model as stated here, and the degrees of freedom will be reduced by the number of variables or number of coefficients we're fitting here. The AIC here is 75. As I was discussing with some other students earlier, the AIC is relative. The AIC for one model compared to the AIC for one data set, for example, compared to the AIC for another data set, another model is different. The AIC for a model for a particular data set compared to a different kind of model where you might transform variables is going to be different. You can't compare those. Here I can compare AIC for nested models. So I can compare AIC for the model with log area and without log area. So I know looking at the outputs here that the log area is a significant variable in the model. I can write down the model equation using that. So I can get here the log of the pi I observed over 1 minus pi I observed. The logistic function here is the coefficient minus, so the constant here is negative 1.19 as in the model there, and it's minus 0.2971 times log of area. I can from there estimate the probability of extinction of a species on an island by reversing the equation, and we've seen that before, so it's exponential of the right hand side over 1 plus exponential of the right hand side. So I can estimate here the probabilities of extinction for each island. The question here is, the size of the island actually affect the probability of extinction? And that's a simple question altogether, because we've seen that from the output anyway. If we're doing this more formally, we're looking at a hypothesis test for beta 1, the coefficient of log area, as beta 1 equals 0 for the null hypothesis and beta 1 not equal to 0 for the alternative hypothesis. We see from the Walls test that the p-value is quite small here, so we'll reject H0 in favor of H1 and conclude that certainly the area or log area influences the probability of extinction. And more than that, what we see here is, because the coefficient is negative, the larger islands have a lower probability of extinction. That's the main question. The larger islands has a smaller probability of extinction, which is really very important from a scientific point of view. Nothing too different here. We've got the logic model here for this regression, simple regression in this case, and we know how it works. Each k-fold increase in x is associated with an exponential here, so it's k to the beta 1. So now that's not so difficult to work out. So you can, there's a bit of maths involved over here. So k-fold increase in x, and it says here with a change in the odds by a multiplicative factor of that. So essentially what we know is that pi is e to the beta naught plus beta 1 log x. That becomes e to the beta naught times e to the beta 1 log x. And by using the properties of exponential functions, what I get here is this is e to the log x to the beta 1, and so this is a power over here. So it's e to the log x this way to the beta 1, and e to the log x actually is just x. This is going to be x to the beta 1. Now if I multiply x by a factor of k, you see what happens over here compared to this. If I have k times x1, what I get is e to the beta naught times kx to the beta 1. And the ratio of these two things, everything else is the same except for the k to the beta 1. So this is going to be e to the beta naught times k to the beta 1. And I get a k to the beta 1 there as well. So the difference here is a factor of k to the beta 1. So the model interpretation requires care here. It does require a bit of maths as well. So if I double x, then the odds ratio changes by a factor of 2 to the beta 1. If I triple x, it changes by 3 to the beta 1. So the odds ratio is not such a simple thing here in this kind of complicated model. Be careful with this. And essentially I've just done that over here in this slide here. You can have a look at this yourself. For a confidence interval here, for beta 1, we can find the limits as the lower and the upper limit. But the confidence interval for k beta 1 then requires us to transform this in this particular same way. K to the lower and k to the higher end. And so this is what happens if we scale by a factor of k. For a k-fold change in x, the confidence interval will change in this particular way. So let's take a look at some interpretation here. So if you double the area of the land, then the change in the odds ratio is by a factor of 2 to the beta 1 in this case, so it's going to be changing by a factor of 0.81. The change in the odds of survival is going to change by a factor of 0.81. The odds of extinction on the reserve land size of 280 kilometers squared is estimated to be 81% of the odds of extinction on reserve of land size A. So as you increase the area, the probability or the odds of extinction decrease. So if I double the area, the odds of extinction are now about 81% or so. And all I've done is the calculations are now out here from A equals 10 kilometers squared to A equals 20 square kilometers of fine. That's what I've said over here. The ratio is going to be, as I've said, the odds of A in both of these cases. You'll find the ratio of those two numbers comes to what I've said it comes to. If you halve, it goes the other way. Then if I halve the area of the land, then the odds of extinction is now 0.5 to that power, the coefficient, and it's 1.22. So the odds of extinction is now 1.22 times, or it's increased by 22%. So halving here goes from 10 to 5, and you can see the ratio of these two numbers. I think you'll find is okay. Confidence interval, we'll look at in the next lecture. Thank you. Bye.